Randall.
Hey, Ilya. Maybe we should, I think this is being recorded. Misha's been on this for a long time. Maybe we should stop the recording and then re-record.
That is indeed. It's empty except for this picture of a mountain.
Yes. Well, nothing should be in there other than the background. Let me start sharing my. Here. There we go. Now it should not be a mountain. Do you want me to stop sharing until you do?
Oh, no, you can just, I think you can leave it on. It's okay. And I figure we'll start in maybe 3 minutes or so. I think we have a good showing.
Sounds good. Let me test my clicker. Good. I'm good.
Maggie, are you on campus now?
Yeah, I live with 6 housemates, so if we all use the internet at the same time, it gets pretty tenuous. So I usually just come to campus when I have an interview.
Yeah. My students did that too this year.
Yeah, but it's thankfully all very, like, we get tested. MIT has a really sort of like good, robust testing system, so it's good. And you have to wear masks everywhere, so it is sort of not in any way endangering, I hope.
Well, I'm assuming that they didn't have any outbreaks at MIT. I mean, at Hopkins, we had something because of like off-campus activities, like frat parties and things like that. But I think on-campus stuff, I think is pretty safe everywhere. Yeah,
I think nothing to my knowledge at MIT, but I've been sort of like seeing, I did my undergrad at UMass Amherst. So I've been hearing a lot of really bad like outbreaks at UMass Amherst. I hope they sort of like get the whole situation under control a little bit.
All right, Ilya, why don't we fire out?
Excellent. Thank you everyone for joining us today for our department seminar. It is my distinct pleasure to introduce Maggie Makar. Maggie is a PhD student at MIT's Computer Science and Artificial Intelligence Laboratory. While at MIT, Maggie interned at Microsoft Research and Google Brain. Prior to MIT, Maggie worked at Brigham and Women's Hospital studying end-of-life care. Her work has appeared in ICML, AAAI, JSM, the Journal of the American Medical Association, Health Affairs and Epidemiology, among other venues. Maggie works at an intersection of machine learning and causal inference, and I can't wait to hear what she will tell us today. Go ahead, Maggie.
Awesome. Thank you so much, Ilya, for the introduction, and thank you for inviting me to the talk. Before getting into the meat of it, I wanted to tell you a little bit about what I've done and how I've gotten here. A lot of the work that I've done and continue to be interested in develops and uses causal inference tools to guide decision-making, or develops predictive machine learning tools to address real-world problems. And while these are all tools that can be used for general applications, I have generally used them in service of healthcare applications, and more specifically in the context of infectious diseases, rather. So how did I get here? The first project that I was ever involved in, we were looking into using healthcare insurance claims to predict mortality. I thought, well, great, we will use these claims to build an awesome, like an amazing machine learning model, and the machine learning cog will fuel the healthcare cog, and greatness awaits for me. But I noticed that something odd was happening, which is that my model consistently suggested that patients who have hypertension are more likely to be healthy and less likely to die. And you don't need to be a physician to know that this does not make a whole lot of sense. But my models had great accuracy, so I figured, whatever, this is good enough for me. And when we tried to apply this model to a slightly different, less sick population, this accuracy broke down. Something in the machine learning cog was missing. And what was missing here is that when filling out insurance claims, physicians had a limited number of spots to write the patient's main ailments. So for patients who are really, really sick, this limited number of slots was filled with things like cancer, dementia, and stroke. But for patients who were not really that sick, there would be enough spaces on their claims to put in hypertension. So this model was really capturing incidental correlations in this particular data set. And that's why it broke down when it was applied to a different population. The missing piece in the sort of machine learning cog is that the model did not incorporate causal knowledge that we know to be true about human physiology. So one big idea that I learned at that time is that predictive models incorporating causal ideas tend to be more robust. The second idea that I learned had to do with intervention assessment. And this is different from prediction models because we're not interested in predicting a target label, but we want to use the observed data to build a model that tells a physician, for example, how their patient would respond to like different interventions or treatments. So what do we do with this data? My argument here is that we need to build causal models in the setting, but I will let the underappreciated causality scholar and 5-time MVP Steph Curry tell you why we need causal models.
New degree dry spray is a game changer, but will it make you better at basketball? We decided to put it to the test. You ready? It's gotta be the dry spray.
So you can imagine the kind of frustration that comes with buying degree dry spray and like expecting to shoot 3-pointers like Steph Curry, but not actually getting the desired effect. In healthcare settings, we risk way more than just frustration. We risk catastrophic events. So what we really need to do is we need to use this data to learn causal models. And we will talk in a little bit about how causal models are different from predictive models, but for now, just trust me that they are not the same. Now, it's easy to think that our perfect causal cog will also move the healthcare cog, and again, greatness awaits. And once again, things are not that simple. The problem is that we typically assume that we have access to large amounts of data when we usually build causal models. So they tend to be inefficient in that they don't make the most use out of small or finite existing samples. And that is a problem in healthcare, especially in resource-limited settings where we don't have money or ability to collect more data. So the great news is that the machine learning community has thought about this question of finite sample analysis quite a lot. And we've developed tools and analysis techniques to build efficient models that make the best use out of finite data. And this brings me to my second big idea, which is that we can use machine learning tools and methods to make causal inference more efficient. And these two ideas tend to shape a lot of the work that I do. So today I will be talking about 2 projects that spans those 2 ideas. And we'll conclude with some future works and future direction that I'm excited about. But jumping right into it, we're going to look first at some work that I have done where we use techniques from machine learning to make causal inference more efficient. In this work, we want to study how we can build models that inform good decision making. So think of an example of a physician who is trying to decide whether or not to administer a certain treatment to her patient. And the treatment may or may not extend that patient's life. What she really wants to know is what would happen to her patient if she gets the treatment or not. And we refer to these outcomes as counterfactual or potential outcomes, and I will use capital Y's to denote them. This is usually referred to as the Rubin potential outcomes framework of, or if you think of sort of do calculus, this is like the outcome of a do calculus. Now, I promised I'd get back to you about why and how causal models are different from predictive models. So if this is something that's stuck in your head, here it is. The important thing about causal models is that these outcomes that we want to estimate are different from observed outcomes because we only get to observe one of them. It's impossible to get a data set where each individual was assigned both the treatment and the non-treatment arm. And this means that we will always have a missing data problem. And that's what we call the fundamental problem of causal inference. And that is why the models that we need to build need to sort of like take into account the fact that the sort of modeling the observed outcomes is insufficient. Now, if the treatment assignment is randomized, we have a maybe data missing at random problem. And that problem is slightly easier. But in most observational settings, the treatment assignment is biased. So for example, sicker patients are more likely to get the treatment, which means that we have a problem of data missing, not at random. So how have we sort of like answered these kinds of questions? When faced with this kind of challenge, people found out that there are 3 assumptions that, if satisfied in the observed data, enable us to identify the potential outcomes despite the fundamental problem of causal inference. So what we typically do is we assume that these 3 assumptions are satisfied in our data, and these 3 assumptions are referred to as strong ignorability, overlap, and consistency. I won't get into the details of these, but if you are interested, please ask offline. Now, if these 3 assumptions are satisfied, we can use statistical tools that manipulate the data such that it comes close enough to a randomized control trial. And if you've heard of propensity score weighting, for example, that's one of the tools that we can deploy here. And with these 2 components, we then usually try to estimate the potential outcomes as accurately as possible. So for the rest of the talk, I will represent the treatment arm with a subscript 1 and the non-treatment arm with a subscript 0. And this gives us the usual goal, which becomes, let's try to estimate these potential outcomes as close as possible, or we try to get as close as possible to accurate estimates for these potential outcomes. And as I mentioned earlier, this approach can be inefficient in that it relies on having so much data. So we wanted to avoid that. So in this work, we said, okay, great. We know we need causal estimates, but do they have to be exact causal estimates in order to inform good and reliable decision-making? Let's go back to the example of the physician. In this situation, asking the model to give us the most accurate estimates possible would be like asking the model to make statements like, the treatment will cause life expectancy to increase by 4 years, 6 months, 11 days, and 2 hours, which, as you can imagine, is often an overkill. And it's often sufficient to say that the treatment will increase the life expectancy by roughly 4 to 5 years. And that's the main intuition behind our work, that in some cases, a rough enough estimate of the causal effect is enough. So in this paper, what we really sought to do is build models that enable us to make statements such as the following. If treated, the patient's life expectancy will be 80 to 85 years. If not treated, it will be 70 to 75 years. Now, let's break down the statement a little bit to get a concrete learning objective. We have that each patient is characterized by an observed set of characteristics, X, and we want to make inference about their life expectancy. So for example, that his life will be between 80 to 85 years. And this first value, 80, is the output of a learned function. And we will use F with a superscript L to denote a lower bound, and a subscript 1 to denote the treatment assignment or the treatment value. This is only one of the functions that we want to learn. We also want to learn an upper estimate or an upper bound for the outcome under non-treatment, or rather under treatment. And we will use F with a superscript 2 and a subscript 1 to denote that function. And similarly, we want to learn the upper and lower bound estimates for the outcome under non-treatment. So we have those 4 estimates that we need. But how are we going to get those estimates? First, we will make the set of usual assumptions that enable us to use observational data to make causal statements. But that doesn't completely solve our problem, because even if we had counterfactual labels, minimizing the mean squared error, which we typically do when we do estimation or typically do in machine learning, would be implicitly shooting to get the most accurate estimate. And we've already established that that might be an overkill. So instead, we will require that these 4 functions achieve what we call a low false coverage rate, meaning the true counterfactual outcome is not lower than the lower bound or higher than the upper bound. So our metric of interest here will be to achieve a low false coverage rate, or FCR, meaning that the probability that the true counterfactual outcome does not fall within the estimated interval is less than some small tolerance parameter rho. So our final learning goal will be to learn meaningful upper and lower bound functions such that the false coverage rate does not exceed this rho. And we'll set aside for a little bit what makes a bound meaningful. We'll get back to it in a bit, but for now we'll focus on finding bounds that have good false coverage rates. Now, I just presented to you two goals. One tries to get the most accurate estimate, and the other is trying to get meaningful bounds such that the bounds correctly cover the potential outcomes. How do we know which one is better? One way to compare those two is by trying to say something about how we expect them to behave on data we have not seen. And this is the part where machine learning comes in. In machine learning, we've developed some really useful tools to study how methods which were trained using finite samples perform on unseen data. Specifically, we want to say something about the probability that the probability or the risk that we make an error on unseen data. So for a given learned function f, we will use r with a subscript f to denote the amount of error we make on unseen data. And this is often referred to as the generalization error risk, if you've heard that term before. And we want to say that this RF is equal to something. But because we're making statements about data that we have not seen, we will never be able to empirically estimate this value. So instead, we're going to try to construct statements that say with high probability, our error on unseen data will be less than or equal to something. Now, for the usual objective, this something depends on the error that we make at training time. So if f has a high error at training on the training data, we expect it to have a high error on unseen data. And the complexity of the true function, and there are many different ways to measure the complexity of the function class, like covering numbers or BC dimensions or Rademacher complexity. But you can sort of intuitively understand it by thinking of how a straight line is probably easier to learn than a slightly nonlinear function, which is probably easier to learn than a very nonlinear function. But yes, so the generalization error will depend on the sort of complexity of the function, and it will also depend on how much data we have at training time. So if we have a very complex function, our only hope for low generalization error is to have a large n. And the problem is that functions, especially in healthcare, are typically very complex. So we need a lot of data, which is not available in resource-constrained settings. So the big question that we had going into this work is, can we do better than that? Can we avoid this dependency on the true function complexity? And one thing that we found is that there is a way to avoid this dependence. So the answer is yes, we can do that. And the big thing that our work has shown is how do we avoid this dependence on the true function complexity. In the next couple of slides, I will show you how that happened and how we arrived at that. Which is on a very intuitive level, our theory suggested that in most cases, just estimating lower and upper bounds is an easier task than estimating the true function. So consider the illustration on the slide. Here we have that on the x-axis, we have like the patient age, and on the y-axis, we have the counterfactual or potential outcome under some treatment assignment T. And the dotted gray line shows the true function with some shaded area, which is the noise. Now, while the true function looks like it is hard to learn, we can use simple straight lines to perfectly cover the counterfactual outcome. The arguments here are sort of symmetric with respect to the upper and lower bounds. So let's look with a little bit more in detail at how hard it is to get a lower bound, just to keep things simple. Here, the generalization risk, which again we denote by R, is defined as the probability of observing a patient outside of the training data, such that the estimated lower bound is higher than the true counterfactual outcome under treatment T. Now, let's say that we want to be extra cautious. And not only do we want this lower bound to correctly bound the data, but we also wanted to bound the data with some margin or buffer region. And that margin parameter we will call gamma. And we will redefine the risk to include this gamma parameter. And this parameter will play an important role in our theoretical analysis. It can sort of be viewed as a measure of confidence. So the larger that gamma is, the more confident that we accurately bound the observed outcomes. Okay, so if the training data has some examples that were not correctly bounded, we refer to the distance between those outcomes and the bound as violations. Ilya, I assume that you will stop me if there are questions because I can't really see the chat box.
I think we may have, I think Betsy may have had a question. Betsy, go ahead if you want to ask it.
Yeah, although I think it was answered on the last slide. Your estimand is Kate here. It's not individual potential outcomes. So I got confused when you said that you want to minimize error on unseen data, but it's error not for individuals, but for Kate. Is that correct?
It's error for the potential outcomes. So this is, we're not taking the difference at any step. This is still sort of like the outcome under a given treatment assignment.
But it's the expected outcome conditional on covariates. It's not like the individual potential outcome for a new person. It's the expectation for different subgroups.
Yes.
Great.
Different subgroups defined by X, yes.
Thanks.
Great, thank you.
Great. Cool. So what we found is that for every value of this gamma, remember this gamma parameter sort of can be thought of as a measure of confidence. What we find is that for every value of gamma, there's an observed data size or data set of size n, and the risk of overestimation of the outcome under treatment T is bounded above by this term, this giant term that you see, with high probability, which is equal to 1 minus delta. And we'll go through it bit by bit. Now, if you've looked at enough generalization error bounds, this first part of the term should not look unusual. The second part, or the second term, appears when we are doing causal inference in finite samples. And why does it appear? Recall that we're making estimates for the general population, but our data is collected from a biased observational data set, or a data set where treatment assignment was biased. So sort of to use ML terms, the second part arises because we have a domain shift. And this term here measures the divergence between the distribution of the general population and that of the subpopulation that received the treatment. So if there's like very high bias in treatment assignment, this term will be very large. And if sort of you have a randomized controlled trial, then this term should go to 0, and this entire big second term that's under the square root should completely cancel out. But to see the core of why it makes more sense to estimate bounds rather than the most accurate possible estimate, it's going to be interesting to look at these K terms a little bit. Now, K has 2 parts. The first measures the complexity of the learning task, and it is controlled by gamma. And the larger the gamma is, the smaller that term is, and the smaller our risk is. Now, remember that if we were going after the usual goal, this complexity term depended on the complexity of the true function. The second term of this K value is the sum of the magnitude of violations on the training data, which also decreases as gamma increases. And the important takeaway here, if I've lost you for a little bit, the important takeaway is that the generalization error is controlled by the margin parameter gamma and does not directly depend on the complexity of the true function class. Now,
hi Maggie, I have quick questions. So when you say here gamma, I assume it's a positive number, right? But when you say the complexity of gamma, so what do you mean? And also the second question is, you have the D2 P, it's KL divergence, or it's like some specific distance you defined?
That is the Renyi divergence. So that is the Renyi divergence, and you're measuring it on the X space. So you're looking at the difference between the covariates or the features of the patients that were treated versus the features of the general population. So that is that term. Gamma, you are correct. Gamma is a positive scalar, but that positive scalar controls the complexity of the true function. If you're familiar with sort of like SVM type things, this is similar to the SVM margin. So the larger that term is, the sort of greater separability in the SVM case, the greater separability you have between the two classes, the easier your task is. Does that sort of make sense? I can try to...
SVM or SDM, sorry?
SVM, V as in Victor.
Oh, okay.
Yeah, so this is very similar to one class SVMs, if that's something that is familiar to, but I can get into a little bit more details offline about that, or yeah, let me know if that doesn't make sense still.
Okay, I think, yeah, I can ask more questions offline, yeah. Thank you.
Sweet, but you're right, gamma is a scalar. All right, so there is sort of something important that I tabled strategically a while back, which is what makes bounds meaningful? What does it mean to have a meaningful bounds? So we can revisit that now. So One example is those two bounds that you see right on this slide. Both of them correctly cover the data or correctly bound the data. And our analysis thus far does not tell us which one is optimal. In a normal setting, I'd ask people to vote, to raise their hands or something, but I will tell you to think about it and make a conclusion. Now, the reality is this was a bit of a trick question. The optimal estimates can vary on an application by application basis. So for example, the bounds in A give the tightest intervals on average, but you might notice that they are wider for younger people compared to older people. In B, the bounds are never too wide for one group, and we have sort of like the same width of interval independent of age. So you can think about this as sort of like a more fair or equitable objective. And ideally, we want an approach that is flexible enough to incorporate these two different objectives. And this brings us to our suggested approach. I will present it at a high level of sort of like abstraction, but feel free to sort of ask me if you want to get into the details. What we do is we maximize some utility function defined with respect to the learned bounds while enforcing the required false coverage rate as a constraint. We plug in different utility functions depending on the applications. So for example, we can make sure that the worst case interval is never too wide by minimizing the maximum interval width. We can also minimize the average interval width by minimizing the squared differences between the upper and lower bounds as weighted by the inverse propensity score weighting, which again, you can think of as like similar to sort of importance sampling and reinforcement learning. Roughly speaking, it is 1 over the probability of receiving the treatment. In our paper, we also show that when we use the absolute rather than the squared differences, we recover the quantile regression for small enough required false coverage rate. From here on out, I will assume that the utility that we're interested in is getting tightest intervals on average just to make life easier for all of us. And there are like a lot of baselines that we can compare to in that context. But before jumping into the empirical results, I wanted to stop for a second to ask, when do we expect our approach to outperform others? It turns out that other bound estimation methods, they try to estimate the true function to the best of their abilities, and then they shift this estimate up and down by some value. And this is what they expect to get. They expect this like nice result. But the problem is that in reality, you might not be able to estimate the true function with limited data. So instead, you end up with this inaccurate estimate of the function. And when you shift it up and down, you get some violation. So our approach outperforms others when there are small samples and we cannot accurately estimate the true function using these small samples. There's another reason why our approach outperforms others. The baselines that I'm about to show you tend to have to make a decision about what makes a good shift. So which one of those two shifts are better? We don't know. And when the baseline decides how to make these shifts, they are implicitly making assumptions about the noise or the residual distribution. So another advantage of our approach is that we do not make those assumptions about the noise distribution. So when they are violated, we are less sensitive to those violations. And there are a number of these assumptions, but the one that I want to sort of bring up, because it's often violated in practice, is the assumption of well-behaved error or residual distributions. What do I mean by well-behaved? This is the assumption that there is some central value, say 0, and the residuals sort of tightly cluster around that value. So for example, they follow a Gaussian distribution with mean 0 and a standard deviation of something. And this is violated when there's heteroscedasticity, which means that the dispersion of the noise is not uniform, say for example, across age, like we see in this illustration. Okay, so let's look at some of the empirical results. How does all this sort of translate into empirical evidence? I will present one set of experiments that we had on one-dimensional data to sort of drive home the intuition, but there are more complicated examples that we present in the paper that I'm also happy to talk about offline. Now, because of the fundamental problem of causal inference, we do not have access to the ground truth labels, and it is notoriously difficult to evaluate causal models. So for this reason, we are going to use semi-simulated data, where we extract the input data from a real data set. So it's nice because it has like some of the messiness of real data, but then we simulate the outcome, which makes it easier to evaluate because now we have access to the ground truth. And this particular data set that we used was a randomized controlled trial. So we also had to introduce some confounding. So in this experiment, what we did is we downsampled the set of older folks who were not treated. So it was simulating a setting where older people are more likely to receive the treatment. As for our baselines, the first one is a Gaussian process with what I'll call typical or classical confidence intervals. And we use the confidence intervals as our bound estimates. And a kernel regression with conformal intervals. Conformal intervals just tend to have better performance than confidence intervals in finite settings because they make slightly less strict assumptions about the distributions of the residuals. This is sort of like work by Larry Wasserman and other people. And all these models that I'm going to present, including our model, these are kernel based. And here we used a polynomial kernel of second order. And in all these experiments, we set the required false coverage rate to be 1%, so 0.01. And here are sort of like the setup for our results. What we'll look at is on the x-axis, we'll see the patient age, which is our sort of like covariate. And on the y-axis is the outcome under treatment. And we're going to look at the achieved false coverage rate, which is the false coverage rate of each model, just to see whether or not they violated the required false coverage rate. And remember here, the false coverage rate that we asked for was 0.01. So anything that gives us higher than 0.01 is not going to be good. And then we're also going to look at the mean interval width. So we want the tightest interval width. So in that column, we want to see lower is better. And the setting that we simulated was a heteroscedastic setting to sort of really highlight the advantages of our model in a place where it could shine. And the black dots that you see here are the true potential outcomes for the test set. The first baseline is the Gaussian process with the classical confidence intervals. That's what the additional C stands for. And we see that it is violating the required false coverage rate by quite a lot. And next in line is the kernel regression with conformal intervals, and it does not violate the required false coverage rate, but it assumes that the correct intervals are constant despite age. And as we will see in a second, it is missing the opportunity to create tighter intervals. The final model is ours, and again, we see that it does not violate the required false coverage rate, and it gives tightest average interval width. There are sort of also more results in the paper on sort of more complicated settings, so I'm happy to talk about these offline. So the summary of what I've just showed you is that there is a way to estimate causal intervals, and it tends to be easier than trying to go for the exact estimate. And we gave sort of an approach to compute these bounds, and our approach tends to outperform other bound estimation baselines. Now, if I just lost you for a large chunk of time, we are jumping into a new section, so clean slate can jump back in with us. And what I've just done is I've presented one idea to use machine learning to make causal inference more efficient. And we are going to move on to another work where I used the idea that machine learning methods, which incorporate notions of causality, are robust against distribution shift. I will only have time for one of those two projects. The project that I will not be able to sort of dig into sort of relates to disentanglement literature in the image domain. So I'm happy to talk to people about this offline if they're interested. And this was sort of like a setting of a recent paper. But what I will dig into is a series of papers. And the first one was published in 2017, 2018, so pre-COVID. In this set of projects, our aim was to build models that take in information about the patients and reliably predict who's going to get infected with a contagious disease. And here, the training distribution is different from the test distribution because of asymptomatic carriers. I think in this current day, I do not need to spend a lot of time explaining what asymptomatic carriers are, but they are folks who are carrying a pathogen that is contagious, but they display no symptoms. And because of that, they are less likely to be tested. One thing that I wanted to say quickly is that this is not a problem that is unique to COVID at all. This is almost ubiquitous to infectious diseases. So for example, the first asymptomatic carrier of typhoid fever was identified in the 1930s. So it's a existing problem. How does this all relate to distribution shift though? Like how do asymptomatic carriers sort of relate to distribution shift? The issue of asymptomatic carriers means that if this 3 people are representative of our full distribution, we have some patients or some individuals who are infected and we'll give these label 1, and some are uninfected and we'll give these label 0, but only some of the infected patients have symptoms, and the uninfected patients, let's say, have no symptoms. During training time, symptomatic patients are far more likely to be tested, so we will have more labeled data for them, and the other 2 groups are vastly underrepresented. But at test time, we apply the model to the full population, and we want to correctly pick up on asymptomatic carriers and differentiate them from healthy individuals. And what usually happens if we're not careful, is that we'll be able to pick up on symptomatic infections only, but not asymptomatic carriers. And there are many reasons why this happens, but the one that I want to focus on relates to how we train our models. In the typical machine learning pipelines, we usually have data and we define a function class. So here, for example, it's a set of all linear functions. And then we feed our data and our function space into an algorithm. And crucially, this algorithm typically looks at a held out validation set and sees which one of the trained models has the highest accuracy on this held out set, and then picks that model as our final model. One thing that we've seen a lot over the last years is that we're no longer operating in this nice, simple function space. We typically consider the full space, which is spanned by different neural networks. So there are, even within a single architecture, there are so many different possible combinations of weights. And then we run into this thing where many of them have really good performance on the held out set. So if our algorithm is only looking at how well we do on the validation set, we will end up with multiple different models that have great performance on the validation set. And this is a case of what I will call underspecification. In other words, the performance on the held out set does not uniquely identify or specify what a good model is. And what happens is that some of these models, these well-performing models, will do well on the extrapolated data, so they'll be good at picking up asymptomatic carriers, and some of them might not be able to do that. So on the bottom, we have like one model that's like with the green tick that's able to sort of capture also asymptomatic carriers, but the other 2 don't. And what I'm here to say is that we can use ideas from causality to ensure that the models that we end up picking are able to generalize beyond the training distribution. To put it a bit more generally, we want to somehow regularize the model such that the final model conforms to some causal knowledge about the data generating process. So basically, this would prevent the model from relying on spurious correlation at training data that cease to exist at test time. And what we're going to talk about next is how to incorporate this causal knowledge. We're going to sort of define some knowledge about the data generation process, which we usually encode in a causal DAG. And a causal DAG is simply a way of defining the causal relationships between different variables that we observed, or even latent variables. Going back to our original function space, we're going to try to penalize models that do not conform to this DAG that we know. So we're no longer just looking at which models do well in the validation set, we're also looking at which ones of them obey the dependencies and independencies that are implied by our causal DAG. And this, in this specific example that I'm about to present to you, we also have auxiliary data that are available at training time. And this auxiliary data is the network of context. And there are probably cases where you can use sort of like the similar intuition, similar technique without relying on auxiliary data. These are, this particular example, we need the network of context. Let's try to follow the recipe that I outlined earlier. Let's start by defining the DAG. So for a given individual, let's call her Jane. There is a hidden or latent state that encodes her true infection status that evolves over time points 0, 1, and 2. And this infection status is controlled by the patient's characteristic. So age, or whether or not they exercise good hand hygiene, things like that. And finally, we have her true infection states, and these are the Ys that we see in the bottom. For this patient, she was tested on time point 2. So we don't really know her infection at the 1st or the 0th time point. Rather, she was tested on time point 1, not 2. And I will use these like dashed nodes to denote that the label is not observed in the setting. And to make this example more interesting, let's say that this patient tested positive at time point 1. And we also have a similar causal DAG for her two friends. Here, neither of them have gotten tested, and we'll assume that we sort of, as I said, have access to the contact networks, so we know they came into contact with Jane at time point 1. And this tells us the important part from the causal perspective is that we know that in order to get infected, you have to have caught it from someone. Jane's contact's latent states have to influence her infection state. And here I'm assuming that we have a direction in the edge, so we know who has influence on whom. And that's a bit of an assumption that we make. So really, knowledge of the DAG here gives us a way to provide soft or pseudo labels for Jane's contacts. So with high probability, one of those two people needs to be infected. And now that we have the pseudo labels, we can use them to regularize, or we can use them to sort of like aid in model selection. How do we do that? Pseudo labeling here acts somewhat as similarly to data augmentation, in that we are adding examples that define how the model should behave on these subpopulations that typically don't get tested. So thinking about it like graphically, on the x-axis if you have some patient characteristic, and y-axis if you have the probability of infection. And this interval here is the values that are underrepresented in the training data, so folks who are unlikely to be tested. There are multiple different models that can fit this part of the input space correctly. But if we have those like additional pseudo labels that are acquired from the causal DAG, then we can define how the model should behave on this interval. And this gives us our final objective, where we iterate between two things. In the first, we find the optimal pseudo labels for all untested individuals for all the time points. And in the second, we find the best predictive model given the pseudo labels that we got from the first step. I don't think I have enough time to sort of like go into the details of that particular example, but this is one of those things I'm also happy to sort of like go or talk about offline if someone's interested in like in exactly how we, what objective we optimize. Cool. So jumping right into the simulated experiments really quickly, what we did is we simulated a universe where there are 3 types of people. Symptomatic if infected, and these are individuals who are very likely to become infected if they are exposed, and they become symptomatic when infected, so they are likely to be tested. Asymptomatic if infected, these are individuals who become infected if they are exposed, but they are asymptomatic, so they are unlikely to get tested. And then the third group is the healthy group, and these are patients who are very unlikely to be infected even if they are exposed. And we will draw the contact network from a stochastic block model, which has a nice properties that allows for some like community structure. To test the empirical performance of our model, we simulated training data with varying levels of testing odds. So you can think of the x-axis as the probability of a sick individual getting tested divided by the probability of a healthy individual getting tested. So on the left-hand side, we have a randomized setting where every sort of like person has a random probability of getting tested. On the right-hand side, we have very biased testing where symptomatic folks are far more likely to be tested. And on the y-axis, we will see the mean AURC on the test set. And I'll present 2 benchmarks besides our main model. And there are more benchmarks that are in the paper, and I'm happy to sort of also talk about these offline. The first one is an optimistic model, which takes into account exposure, but it assumes that everybody who was untested is also uninfected. And there's the no exposure model, which completely ignores exposure and only relies on individual characteristics to get an estimate of the infection. And what we see is that our model outperforms baselines on almost every level of bias. And at high levels of bias, we perform as well as the baselines. And this happens because our model is better able to impute a good enough label for the untested individuals, which effectively increases our sample size. At extreme levels of bias, everybody does roughly equally well. The last thing that I wanted to talk about in this project is some real data experiments. On our real data task, we want to predict the onset of Clostridium difficile infections among patients at a large urban hospital. Clostridium difficile is a bacterial infection that attacks the gut. And in really bad cases, it can lead to death, but it imposes a huge burden on the sort of like healthcare system in terms of costs and mortality and complications. So it's a real issue that has been ongoing for decades. In this task, we extract daily labels, medication, or rather daily lab procedures, medications and sort of like procedures from the electronic health records. And we also extract contact networks based on nurse and room sharing. Here we don't have access to the true labels like we did in the simulation. However, we can create a proxy label for the asymptomatic carriers as follows. There are two types of tests that are used to identify C. diff infections. There's a toxin test, and if it comes back inconclusive, another highly sensitive test, a PCR test, is used. And there's a lot of discussion in the medical literature that patients who test positive to the PCR only tend to be asymptomatic. So we use that as a proxy. So for patients who are toxin positive, we take them to be the symptomatic patients and we reveal their label at training time. Asymptomatic carriers we define as those who are PCR positive. At test time, we ask the model to sort of predict both the PCR and the toxin positive. And what you see here is that these are sort of our metrics on the held out test. So there's the AURC and there's another metric, which is the true positive rate at a false positive rate of 10%. The first one, the AURC, we're doing better than the other two baselines, and it just tells us that we're better able to predict patients who are infected. The second one is the true positive rate when we pick a classification threshold that achieves a false positive rate of 10%. So at this level of false positive rate, we are able to identify 15% of the infections more than the other baselines. And this metric is important, and I think it's more meaningful to look at than the AURC, because our medical collaborators often ask for something that has low false positive rates. They don't want a model that will sort of like cry fire at every hint of smoke. So this is sort of like a more meaningful metric for them. Now, again, if I've lost you for a bit, in this last part of the talk, I showed you how we can use knowledge of the causal tag to make machine learning models more robust. There is a number of applications where we can use these kinds of contexts. One is the prediction of infectious diseases, which I talked about, and another one that I'm happy to talk about is offline is image classification. Okay, so wrapping up that part, I want to talk to you next about what I'm excited to work on going forward. Broadly speaking, I'm excited to continue working on developing theory and methods at the intersection of machine learning and causality. And I also want to develop and build models that impact healthcare in meaningful ways. Quickly outlining some of these future directions. When we think of regularization as machine learning folks, we typically, either through like implementation or even reasoning about theory, we typically think of what I refer to as mechanical regularization. So saying something like, okay, I want the norm on my weight vector to be bounded above by some value A. And from a theory perspective, we can take that and translate it into knowledge about function complexity or the size of the function space. Meaning we can say that the metric entropy or the size of the function space is smaller than something that depends on the bound on the norm. And several recent literature, and certainly my own experience, points to the notion that these mechanical methods of regularization don't really work well for deep neural networks, especially when we're thinking of distribution shift at test time. And that's why I think we need to move on or like need to incorporate more conceptual or causal knowledge-based regularization. So this is something that I want to continue working on, and especially to like reason about how this kind of regularization affects or regularizes the function space. What kinds of statements can we make about our metric entropy or the size of our function space if we use this kind of regularization? Another thing that I would like to work on is, if you recall from the illustration from before, these different performant models that we get in the deep neural network pipeline, each one of them implicitly encodes a different DAG. So the question here is, can we identify what these different DAGs are? Because they have different implications in terms of like interpretability or fairness, or they might have different implications for the final decision maker. And these two questions are more related to the causal side, or incorporating causality for machine learning side. For the other side, for machine learning for causality, one of the things that I've thought about a lot is how do we cut corners or in a sense, like how do we create minimal causal estimates that only address the decision maker's needs. And one other area that I want to continue thinking about is causal inference in the presence of interference, or this is the case when we have like infectious diseases. And I think this is an area of a lot of promise because in many situations, we only need a crude estimate of the causal effect to achieve the final goal. So that's another area that I'm excited to work on. But all this, like all the stuff that I've talked about in terms of developing theory and methods for machine learning and causality is different, or is definitely interesting on its own right. But I also think that these are tools that are necessary to address real issues in healthcare. So when we develop the generalization error of some model, what we really want to know is how much can I trust this model when applied to high stakes problem in healthcare? And the thing that I've learned over numerous collaborations in healthcare is that defining and choosing the right problem is at least as important as building these models and their theory. And the set of problems that I believe can have a significant impact and where I want to concentrate my effort is the set of problems that address issues that physicians don't know. So for example, a physician is very well trained in giving prognoses based on a patient's symptoms, but it's very hard for them to quickly sift through days and days of data and realize that, hey, my patient is in a room that was occupied by an asymptomatic carrier of C. diff, so they are at a higher risk of C. diff. And this puts us in a bit of a bind because you cannot sit down with a collaborator and ask, what do you not know? Because people don't know what they don't know. So that's why I think problem scoping in and of itself is a very difficult research question. And I think when I think about wanting to make a real impact in healthcare, I think starting with problem scoping is really the most important thing. So obviously, thanks to the tiny army of collaborators that I have, and thank you for listening, and I'm happy to take any questions.
Great, thank you, Maggie. So let's open the floor for questions. While folks are gathering their thoughts, maybe I could get things started a little bit. So your work in bounding the Kate. So you're assuming ignorability as usual given. So is that given the X that you actually end up estimating, or could X be a subset, or what is of what you need to adjust for all confounding, or what?
X is, I assume that all the variables that we need to adjust for confounding exist in X. Yes. They could be a subset.
You haven't thought about the subset, X being a subset for your surface.
Yeah,
okay,
yeah, I haven't thought about like what happens if you're conditioning on something like an instrumental variable, or what happens if you're conditioning on variables that you really shouldn't condition on. There's definitely like more work to be done in that area, but it's not something that I've thought about, at least in the context of this work.
Okay, great. Raman, go ahead.
So I had a question regarding what you said about regularization. Mm-hmm. So, one of the reasons what you call mechanical regularization, norm-based complex images, is useful besides capturing, something nice geometric about, giving us some geometric intuition about the complexity of the models, is that they lead to tractable computational approaches. Mm-hmm. When you say you want to use causal models or some kind of causal regularization, mm-hmm. Can you say a bit more about what you mean? Because the way I think about these objects, they're discrete mathematical objects mm-hmm. like DAGs. So
yeah. So some of the work that I wasn't able to talk about today, we use MMD, the maximum mean discrepancy, as a way to regularize. So maximum mean discrepancy just measures the distance between two probability distributions. So in that particular example that I'm talking about, this was a case where we knew from the causal DAG that a specific independence should hold. So our prediction should be independent to a specific variables, let's call it that. That's a sort of like simplification, but that's it. In that case, we needed to compute the MMD in order to sort of like regularize our model. the MMD is computable. Like we can approximate it using kernels or kernel methods. But you're getting at an interesting point, which is even the MMD estimate is sort of prone to errors. So when you think of the mechanical regularization, when you have the norm of your weights at training time is 5, your norm at test time will be 5. But when you are minimizing something that is dependent on data properties, that means that you are prone to error even in your regularization term. And that's something maybe.
So maybe I'm to understand that you're suggesting that some notion of data-dependent complexity measure would better explain the performance. So it could be based on some causal knowledge we have about the models, but really what you're emphasizing is some so data-dependent generalization bounds, for example, in ML would be desirable.
Yeah, yes, that's sort of like putting it succinctly.
Thanks.
Great. So Raman raised his hand, like the emoji. So if you have any questions, please just speak up or raise your hand. In the meantime, while people are thinking about this, Maggie, so you're bounding things that are complicated, right? So there are lots of cases where you might want to do this, right? So for example, if I have semi-supervised problems in machine learning where I don't have the labels, maybe you would want to do it because it sort of seems similar to the Kate, or your colleague Alex Demore, who you have some work with, wrote this paper on lack of reliability in predictive models because of various complexities with that. And so, have you thought about applying this kind of work? So it seems that the spirit of your work there is, let's assume something simple and bound above and below the surface we're interested in. And this seems like a very generally applicable idea for lots of things ML people worry about, right?
Yeah, that's true. And yeah, I have thought about it, and it's very interesting. Like, I think the majority of that work can be stated in an entirely non-causal setting. Like, you can think about bounds in general in like finite samples, even if you're doing like straight up predictions, not relating to any causal settings. And I think that's actually one sort of tail of this work that I would like to address. There is existing work similar to that. Like there's Larry Wasserman's work on sort of ambiguity sets is what he calls them. So when you're trying to like predict a label, like let's say you have multiple labels, so it's like a one-hot encoding, you can, instead of trying to go for the most likely label, you can go for an ambiguity set. So saying like this sort of like classification or this example can be classified as one of many in this small set that I'm giving you. So there is existing work, but I do think that we can add to it a lot using sort of like our work. So it's definitely something that I'm very much in the very near future hoping to sort of hammer out once this whole thesis thing is out of my way.
Okay, thank you. Sorry, just one more quick question. So do you explicitly assume data dependence when you incorporated sort of DAGs to represent disease transmission? Like, I didn't quite get a sense of whether you explicitly just didn't have an IID likelihood in that when you were training.
Well, so what we do here is we assume that conditional on a patient's X's, so conditional on the patient characteristics, as well as their neighbor's infection states, you get conditional independence.
Okay, I got it. I understand.
Yeah.
Thank you.
So the idea is like if you can get really good pseudo labels, then hopefully you can get like really accurate X's or X's is completely observed, but you're also getting like a really clean estimate of your neighbor's context. So that allows for this conditional ignorability to a sense. I hesitate to use like causal language to describe that because it's very predictive. Like I don't think, I can't make causal statements about that kind of model, but similar ideas.
Okay, great, thank you. Dan, did you have a question?
Sure. Presumably a doctor is going to use a lot of covariates, right, in making decisions for a patient. And, it could be fairly high dimensional. Do you have a sense of how much data, you talked about how you're making more efficient inferences, in finite samples. And do you have a sense of how much data is needed and how that relates to how big X is? Are we talking about 1,000 patients? Are we talking about 100,000? Are we talking about 1 million? Where are we at?
Yeah, so the answer that I'm going to give you is probably going to be unsatisfying. It will depend on, in a normal setting, the answer to this question would depend on how complex your true function is. And honestly, that's like not really an answerable thing because you don't really know, like in primary, what is the complexity of your function. In our setting, it will depend on confidence, like how much, if you really, really need, I'll give you sort of like a trivial example. If you need the bounds to hold with very, very, very high confidence, you can get away with having very, very, very little data, because I'll give you confidence bounds, or like bounds that are very, very not tight. So just like make them super like wide.
Sure, but that's not going to be useful for a physician making a treatment decision. So
yeah, so
we
that was
have to make a treatment decision. We want to be able to, right? Yes,
for sure. And that's sort of our approach sort of at least sets a trade-off between saying, okay, if you have, or rather if you want really, really high fidelity, so like low false coverage rate, that trades off with sort of how tight your bounds can be. So in that sense, I can't tell you exactly like how many data points I need, and our bound does not depend on it doesn't depend on like how big your dimension is. So that never appears in the bound. It just sort of like gets pulled into the function complexity argument. But there are ways to measure function complexity that are dependent upon the dimension. So the input dimension. That's not something that I have explored a lot.
Yeah, I think it would be useful to actually do this with real data and see what see what you can get out of it.
The problem is, yeah, so that would be really great for a pilot study, like, because I don't think, like, to see what comes out of it, you need to have someone implementing something, or like a physician looking at the results to sort of like say something, because again, there's no easy way to validate causal models absent strong assumptions. So that would be something that I'd be very, very interested in, to sort of like look at actual medical applications in that. That paper, we didn't have a direct medical application. It wasn't like real data that we worked with. It was mostly simulation, but that would be, yes, that would be really awesome.
Thanks, Maggie. I really enjoyed your talk.
Thank you.
All right, I think we have time for maybe one more question, if anybody has one. Jason, maybe you have one?
Sure, I can ask something. So this is a little bit out of left field, I'm afraid, but there has been work about something that looks kind of like causal regularization in the reinforcement learning community. So I'm thinking of like Pinto's work on influence functions, where you say that certain actions were unable to influence certain subsequent rewards.
Yeah, so a lot of the questions in causality, to me, or rather a lot of the questions in reinforcement learning, especially in offline reinforcement, ring to me like questions about causality. So I'm not surprised at all that there are similar things. I'm not familiar with that particular work that you mentioned. Do they say like, oh, some part of the state space is not really important for estimating the reward? Is that what it is?
This is actually asking about which earlier actions can affect later rewards. So it's directly between actions and rewards, skipping over the states.
Yeah, so that seems like, okay, in that case, it seems like...
Think about policy gradient, I guess, is the right...
Yeah, so it seems like what the statement that they're saying is that you can sort of ignore a large chunk of the history, and it wouldn't really affect... Yeah, so that's really interesting, because it's something that I've thought about a little bit, which is you have like effect modifiers or mediators and causal estimates that are meaningful, and there are some variables that don't affect the sort of like the treatment. They don't interact with the treatment to cause a different estimate at all. And these would be really good to sort of like ignore, because we now know that like ignoring them does not really affect our estimation at all. So that is really interesting, and it's something that I want to be very careful about, because I feel like there are a lot of regularization schemes for causality that I'm not like this is, I have to be explicit about this. This is not what I'm suggesting on that slide. What I'm suggesting on that slide is using ideas from causality to regularize prediction models rather than sort of thinking about how to regularize in the context of causal models. There's a slight distinction here that I don't know if that makes sense. Does it?
Yes, it does.
Okay.
Thanks.
All right. Well, I think we're basically out of time. So join me in thanking Maggie for a wonderful talk. I'll try to clap. I don't think it's quite the same though. Remotely.
I feel it. I don't hear it, but I feel it.
Feel the excitement. All right. Thank you, Maggie. And we'll talk later.
Thank you.